Okay, so we're going to go ahead and calculate the pH of a strong acid, and I'm going to show you the real quick shortcut method, and then I'm going to show you the why we can use the shortcut method. So kind of the long cut, but it's really not that long. They're pretty quick anyway. So this is a strong acid. How can you tell that you have a strong acid? Well, if the Ka is greater than 1, your acid is strong. So this one has a Ka of 10 to the fifth. This is hydrochloric acid. We have a sample here of 0.2 molar hydrochloric acid. And even if you're not given a Ka. Usually, you won't be given a Ka for a strong acid. But there's only 6 strong acids that you will probably see. Uh, those could be hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, nitric acid, and perchloric acid. So these guys are only strong acids. Everything else is a weak acid, and you need a Ka for that one. Here, you don't need a Ka because basically the equilibrium constants are so big that essentially these things go to completion. So let's go ahead and just do real quickly the shortcut version, the really fast version of how to do it. Right? So remember, in order to calculate a pH, right, what we're looking for is what is the pH of this solution. Forgot to put that up there. That's the question. What is the pH of solution? In order to calculate the pH of the solution, what we need is the hydrogen ion concentration. So what we're going to need here is to figure out what the hydrogen concentration is. Right. So we need this right here. Okay. How do we get the hydrogen concentration? Okay. Essentially, on a strong acid, your hydrogen concentration is just the initial concentration of the acid, whatever it is. So in this case, our hydrogen concentration here is going to be whatever the concentration of your acid is right there. That's not true for a weak acid, but it is for a strong acid. So the hydrogen concentration is 0.2 molar. That's it. Now plug it into your formula right there. pH equals the negative log of 0.2. And what we get is, let's see, then the log of 0.2 is, here it is, negative 0.69, basically negative 0.70. All right, so I'll go back to 0.70 since we rounded it off. And since that's negative, and we need to take the negative of that, our pH is 0.70, right? Ooh, that's really small. Okay. And that's it. You're done. All right, so whatever this was right here, that's what you put into your pH formula. That's your hydrogen ion concentration. That's what you put into pH formula, and then you can figure out your pH over here. Um, so that was quick, right? And so strong acids really are the easier problem because you already have the numbers. You just plug into the pH formula. Now, why is that? At this point in time, if you don't want to know why, you're done. You can do the problems, right? But if you want to know why, I can show you, and it doesn't take too long. Okay. So let me go ahead and show you how this works. All right. So HCl here is an acid, and just like any acid, it's going to break up into its ions, H plus and chloride. Okay. And we can go ahead and make that L a little bigger, a little bit better. As usual, we can make an ice table here that gives us initial change in equilibrium concentrations. And we started with a concentration of 0.2 molar for HCl, right? So we're going to start off with 0.2 molar. Okay. And we put 0 hydrogen ion and 0 chloride ion. Okay. So you'll recall that whenever we have an equilibrium calculation, we don't know how much of our initial concentration here is going to turn into hydrogen and chloride. So normally we'd put minus X and plus X and plus X. Okay. We're not going to do that this time. And the reason we're not going to do it is because we know how much is going to dissociate, and it is all of it. In a strong acid, all of the initial concentration dissociates. So minus 0.2 here, because the coefficients here are 1 and 1 and 1, okay, because they're all the same, then we know that they're equal molars. So if we lost 0.2 moles per liter of HCl, we're going to gain, oops, forgot to change here. We're going to gain 0.2 moles per liter of hydrogen, and we're going to gain 0.2 moles per liter of chloride. And so once we hit equilibrium, there will be no HCl left, and there will be 0.2 moles per liter of hydrogen and 0.2 moles per liter of chloride. And so now, this right here is our hydrogen ion concentration. Notice it's the same number as it was here. So for a strong acid, you can assume that all of your acid is going to turn into the ions, and you'll be left with nothing here at the end. Okay. Now, some people say, but wait, isn't this an equilibrium? Yes, there's an equilibrium, but since the K is so big, remember that it's Ka is concentration of the products over multiplied together times over the concentration of the reactant. So in this case, HCl. Since this is 10 to the fifth, it's so big, it favors the product so much more than it does the reactants. Actually, I did this calculation. If I did an equilibrium calculation, I did it a little while ago before doing this. And if you did an equilibrium problem, what you're going to get for concentration of HCl at equilibrium is going to be 0.0004. Yeah, so that'll be, no, actually, I think there's going to be one more zero. Goes to the fifth. Okay, so that's the number you get. But, compared to 0.2, this number's minuscule. And if we said this is minus x and plus x and plus x, we would have found that the x was going to be some number like, 1.99996. And so if you went ahead and got 0.2 minus 1.9996, you'd end up with this number here. And over here, you'd end up with, 0.19996. Essentially, you round it off, it rounds back to 0.2. So why bother with all that? Okay. You're basically going to, unless you round off to, 5 decimal places, you're going to round back up to this number here. So why bother with it? And so that's why you can go ahead and take that shortcut. Whatever this number is right here, that's going to be your hydrogen concentration. It's going to end up over here. And so that's what you use to do your calculation over here. Okay. So that's how you solve strong acid problems. Okay. All you have to do is know that you have a strong acid. One of those 6 over here on the right. Or you're being told Ka greater than 1. Or you're just told you got a strong acid. Then whatever the concentration of the acid is, that's also the hydrogen ion concentration. Plug that into the pH formula, you're done.